In the last lesson, we looked at the fundamentals of chemical reactions and what controls their rate, and we've discussed those. Today, we're going to look at how you determine the order of the reaction in some of its components. One of the ways to do that is to do initial rate studies. And what that means is you are measuring the change in concentration over time. And we're going to look at that. It would change as the reaction proceeds. In the beginning, it's going to have the fastest rate, the most negative slope. And then as the reaction gets further and further along, the rate decreases typically because you're using up the reactants. And so the rate at time zero is what we call the initial rate. So what you would be doing is plotting concentration versus time. And then at time zero, you draw a tangent to that line. And from the slope of that tangent, you can get the rate of the reaction or the rate at that component is changing at zero time. And then, of course, we can convert that to the rate of the reaction at zero time. So if I have one experiment where I'm going to start out with certain sets of concentrations, I'm going to do another set of concentrations, and that would be my experiment number 2. Each of those would be equal to a constant times the concentration of that species raised to its power. Now you can see by this that the rate constant cancels out. And so you wind up then with a ratio of concentrations raised to the order power. So if we have measured this number, and we've measured the rate at experiment 2, we measured the initial concentrations for experiment 1 and the initial concentrations for experiment 2. We know everything in this except alpha, and we can then solve for alpha. If you take the logarithm of both sides, you would get the log of the rate for experiment 1 over the rate of experiment 2 divided by the log of the concentrations ratios. So that's the general method we can use to solve for that coefficient at time zero. And you can also do it by plotting some function of concentration versus time. And what we would have for a zero order rate reaction would be the rate would be some constant times concentration to the zero power. So the rate is just equal to a constant. So if you looked at the way the concentration would change over time, you would start out at initial concentration, and then for every moment of time, you multiply that by the rate constant, and that would give you the final rate at that time. So you would be plotting concentration versus time, and you'd get a straight line if you did that. And so what you would have is, if you made this kind of plot, the concentration versus time, if it's zero order, the data will be linear. So you wind up with a straight line, and you could calculate then what the slope of that line is, again, by taking the rise and dividing by the run. Now, I'm being a little more precise here because I want to tell you, do not use any 2 of your data points to calculate the rate, not even 2 data points far apart. What you're looking for is you draw the best fit straight line between your data points, and then you look over on the left top and see if you can find a place where the line you have intersects the vertical and horizontal grid lines. So this would give you a point here, and then you look for a similar point far away from that one. On the other end of the graph, you find a point where the line goes through the intersection of your vertical and horizontal grid lines. And then you'd measure the rise between this point and this one. And you'd measure the run between this point and this one. And that would give you the slope. And the place where the line hits is the intercept. And if you're looking at this kind of graph, the equation for a straight line is y equals mx plus b. Y is going to be the value on the y-axis. The x-axis is the time axis. So the k in front of the time is going to be the slope of this straight line. So the slope is minus k, the slope is negative, and the constant is taken as a positive value. The intercept is just going to be A0. So if you made a graph and of concentration of A versus time, and it is linear, then that proves you have a zero order reaction. None of the other orders would do that. Only zero order gives you a straight line. I do want you to notice also something about this type of reaction. It's definitely over at some particular time. The concentration will drop to zero at some time. You don't see that in other reactions as well. So if I plot a graph of concentration versus time, and it's not linear, what it tells me is that it's not zero order. It doesn't tell me that it's some other order. It just tells me it's not zero. Now, let's suppose we had a first order reaction. Well, the first order reaction will give you a rate is some constant times concentration raised to a power. And if you did the calculus on this, I'm just going to give you the result. You get an equation, log of the concentration at any time is the log of the concentration at zero time minus KT. So again, this can take the form of a straight line. If the log of the concentration is plotted on the y-axis against time on the x-axis, then the slope would be minus k, and the intercept would be the log of A at time zero. So thinking about the practical nature of the experiment, I would make a column of concentration versus time, and I would measure how the concentration changes over time, and that would give me two columns of data, time and concentration. Now, if it's zero order, I would plot those two columns, with concentration on the y-axis and time on the x-axis. That would be the test for zero. If that's a straight line, then you're done. You don't need to test any other order because you already know it's zero. But if that one is curved, then you make a new column on your data. You take the log of each concentration and put that in the next column. So you now will have a column of time as one column, and log of concentration at each time is the other column. And now I can graph that. If I plot this on the y-axis and x on the time on the x-axis, it could be linear. If it is linear, then that tells me this relationship is holding, and it is first order. So again, I would plot log of concentration versus time. I would get a straight line if it's first order. The slope of the line, again, we would determine as before, find a couple of good graph points, measure the rise and the run, and then divide the rise by the run, and that would give us the slope. Slope is going to be negative in this case. And so if I do see this behavior, log of concentration versus time is a straight line. Now I don't have to test any other order because I know it's first order. And if it's not linear, if this is curved, you notice we've got some scatter in the data, but it's statistically random across the line. Now, all of these missed points were on one side, you might think, well, that's almost linear. You could make a line, a straight line through it, but that's not a straight line. A straight line would have, your error would not be systematic. If these points between those two endpoints don't fit on a straight line, don't try to force it to be a straight line. It's not a straight line. It's a straight line only if your data scatters randomly across that line. So once you've got the order, you're done with the experiment. What if this one is also curved? Then it's not zero and it's not first. We've already tested both of those. Let's look at second order. The second order equation is rate is concentration raised to this second power. And this is an equation you can solve in calculus. I'm going to give you the result. So if I take 1 over concentration at any time, that would give me 1 over the concentration at 0 time plus KT. Now remember, the concentrations are in the denominator. So 1 over A at time 0 is going to be a bigger value than 1 over A at any other time. And so this, this reciprocal, since concentration is going down with time, this change in that is going to be a positive number, not a negative number here. So again, here's the way you make the graph. You would plot this 1 over concentration at any time as the y-axis component and time as the x-axis component. And so you would have an equation in the form y equals mx plus b, which is a straight line. And the slope and the intercept would, would give you the specific rate constant. And so you get a graph that would look like this. And you know, this one's going to increase over time. We would again put our best fit straight line through the data points. And we would find a couple of good graph points to use for the rise and the run to get the slope. And we can calculate the slope. The slope is going to be equal to K. So if a graph of 1 over A at any time versus time is not linear, then it's not second order. So it has to be one of the other orders. So we figured out a way how to get 0. We can test that directly from the concentration versus time, make a graph of that. If it's linear, we're done. If it's not linear, you would create another column. That column would be, for each time, we would include the log of the concentration at that time and create a second column that had log of concentration. And then if neither of those happen to be linear, then we need to make another column. At each time, we would take 1 over the concentration at that time and enter that as a column of data. So, and then we would make a graph of 1 over concentration versus time. If that's linear, then it's second order. For us, one of those 3 plots will be linear. Now there's another way that we can get the order of reactions from what we call half-time data. How long does it take for half of the concentration you currently have to disappear? That's the half-time of a reaction. Let's look at that in 0 order reactions. If you do that, we would have a plot that would be linear when concentration is time. So I could go into the data and I could determine the initial concentration and the slope. And now if I go down to half of that initial value and go over to the graph and down to the time, that is the half time for that reaction. It's the time it takes for half of your original concentration to go away and leave half of it still there. Now that would be 1 half time. If we now start at this concentration and see how long would it take for it to go to half of that value, that would be 1/4. Then what you would get is 0 concentration. So the zero order reaction is completely over at 2 half times, because it takes the same amount of time to go from here to here as it would take to go from here down to 0. All right, now, so 0 order reactions will be complete in 2 half times. The reaction is completely over. Now let's look at first order reactions. A first order reaction, this is synthesized data that is accurately and is calculated from a real first order kinetic reaction. We start at some concentration. I'm calling it 1. It's 100% of what we started with. And we could perhaps go to 0. And this is time along this axis. I don't have units on it, but it could be minutes or seconds or hours or whatever. But now let's look at the idea of a halftime. To go from 1 to 0.5, in this particular case, took 2 minutes, let's say, 2 units of time. Now, if I go from 0.5 to 0.25, it will take the same amount of time that it took in the first halftime. So each halftime is constant. It takes 2 minutes to go from 100% to 50%. It takes 2 minutes more to go from 50% to 25. It takes 2 minutes more to go from 25 to 12.5%, and so forth. So if you notice about the first order reaction, it's never really going to be complete, because whatever your concentration is, you're going to still have half of that left after 1 halftime. So if the halftime is constant, then this is a first order reaction. So if I went back to my first column of data and I saw it's not linear, it doesn't take the same amount of time for the concentration to change by the same amount. That's not 0. But if I look at how long it takes to get half of it, and then I say, okay, double that time and see if that's the time it takes to get from 50% to 25%. If that's true, then I know it's probably first order. And what I would do then is just make the first order plot, not even make the second one or the 0 order, because the data is indicating it's probably first. If I didn't do that and make the plot and it's linear, then I know that confirms that it is in fact a first order reaction. So the characteristic of the first order reaction is that each halftime is the same amount of time. It takes exactly the same amount of time to go between any concentration and half of that concentration, no matter whether you're right in the beginning or near the end of the reaction. That would always hold for a first order reaction. All the halftimes are the same. Now, what if we had a second order reaction? In a second order reaction, I have the same data now plotted on a second order reaction. And the second order reaction also has an interesting feature. The time it takes to go from 100% to 50% is your first halftime. But notice the second halftime is not the same as the first one. In fact, it's going to be exactly twice as much as the second one, as the first one. If the first one was 2 minutes, the next one is going to be 4 minutes. 6 minus 2 is 4. So the second halftime is twice the first one. Have you guessed what's going to happen the next one? If it's second order, the second halftime is going to be this next halftime, the third one, is going to be twice the second one. So if the second one was 4, it's going to be 8. So it would go from 6 minutes to 14 minutes to get to the second halftime. So second order reactions start out very fast and slow down as the reaction goes on pretty dramatically, because each halftime is doubling the one before it. So this is a characteristic of second order reactions. So again, if I looked at my data and see how long it takes to get from 100% of my initial concentration to 50% of that, I can see on my data how many minutes or seconds it took. If I go from 50% to 25% and I see how much time that took, if it's the same as before, that's a first order. But if it's near twice as much, that's second order. And zero order, of course, would be over at that time. So you can look at half times then and make a pretty good judgment from your original data what the order is. And then you can make the plot that you want to make to confirm that it is either zero or first or second. Now, let's look at some problems with this. And here are some initial rate studies. And we want to determine the experimental rate law from this data. Well, now why did I pick reaction 2 and 3? Because I looked at my data and I made this concentration the same as this one while I varied this one. By doing that, this concentrations are the same, so since they appear in a ratio, then I know that if I look at this number is rate 3, divided it by rate 2, from that I got a 2. So the ratio of the rates is a 2, that has to equal to the ratio of the concentrations. Concentration here, I also made this one twice that one. So this is a 2. So 2 to the beta has to equal 2. Well, that means beta has to be 1. So in this case, by picking these two, I now know the rate law has B as first order. Let's continue. Now to get the others, we'll just ratio this one that we haven't used with either one of these two. I picked number 1, and I always set them up with the larger rate on top. This is a bigger number than that one, remember, negative exponents. So if I set them up like this, divide that out, what I come out with is 4. All right, so the ratio of the rates is 4. So I know the ratio of the concentrations in run 2, A, this is 0.64. In run 1, it's 0.32. And this is still raised to the alpha power. I don't know what it is yet, but I do know what B is. So I put in the concentrations of B, 0.046 in run 2, divided by 0.023 in run 1. And now that's raised to the first power. I've already determined that. So I have a relationship. 4 is going to, this divided into this is a 2 to the alpha, and this is a 2 also to the 1. So I can divide these out. Alpha then is going to be 1 also, because 4 is 2 squared. This is 2, so alpha needs to be a 1. When I multiply two numbers, I add their exponents. So in this particular case, the rate law gives me a constant times concentration of A to the first power and concentration of B to the first power. Now, we can also get the rate constant, because you see, if I took run 1 and I put in the concentration of A at 0.032, concentration of B at 0.032, and the rate is 5.1 times 10 negative 7, I can solve for the constant. And one of your tests to see if you've got the rate law right, you should get the same constant in all 3 runs. So if you use this set of data and get a rate constant, and then use run 2 data to get a rate constant, and use run 3 to get a rate constant, all 3 of your numbers should be the same number. And if your rate law is correct, that will happen. Okay, now here's a problem that you should try on your own. And again, I've set it up so you can pretty easily see that you want to start with run 2 and 3 again, as we did, and determine all of the information about that rate law from these data. Okay. Here's another problem. Dinitrogen pentaoxide decomposes to dinitrogen tetraoxide and oxygen. The rate is first order in N2O5 with a specific rate constant of 6.22 times 10⁻⁴ at 45 degrees Celsius. Remember, the temperature also affects the rate. So if we have a rate constant, we need to know what temperature it was at and make sure the temperature remains constant. What will be the initial rate of formation of oxygen if the concentration of N2O5 is 0.1 molar? Well, we've got our reaction written down. We know from the given information that it's first order, so the rate is K times N2O5 raised to the first power. And we are told that that rate is 6.2, the rate constant is 6.22 times 10⁻⁴ seconds minus 1. The concentration is 0.1 molar, and the order then is the order is 1. Okay, so the rate of oxygen formation is going to be that times the balancing coefficient. I went a little too fast with you on that one. So we're going to take 6.22, and if we are told that the rate, for oxygen, it's going to be the same value because you see we were looking at a coefficient of 1. So it would be rate divided by 1. So it's going to be the same thing. For the others, there would be the rate divided by 2. Each one of these had a 2 balancing coefficient. Okay. Same type of information. How long will it take for the concentration to go from 0.1 to 0.01 in this reaction? Well, if it's first order, the relationship is the log of N2O5 at any time is the initial value minus K times the time. So I have my data. The concentration that I wanted is 0.01. What I started with was 0.1. I know the rate constant. I can solve for the temperature. I think 3,700 seconds. That's a pretty long time for that to happen, but that's what the data says. Now, okay. Again, we're using the same relationship, and we want to know what would be the concentration after some time. In this case, 100 seconds. So I'm still using the first order rate equation, integrated rate equation it's called. I know the value of the initial concentration. I know the rate constant. I know the time. And make sure the times are the same units. Second minus 1 times seconds is 0. You can't take the log of a number with a unit. So when I plug in the data, the log of 0.1 is minus 0.2303. This times 100 is this. So I can solve for that. It's 2.36479. And now to get rid of the log function, I raise everything to the e power. E to the ln of something is just the something. And so the N2O5 concentration at 100 seconds is e to the minus 2.3647 is 0.094 concentration. So we started out at 0.1 and it took 100 seconds, we only got down to 0.094. So it takes a long time for this reaction to go. What is the half-time? Well, now the half-time, you can rewrite it like this. And it's an easy calculation you do. You just get the concentration at time 0 is let's say it's 1. Concentration at halftime is 0.5. So you're going to take the log of 1 over 0.5 divided by k. That gives you log of 2. And this is going to be characteristic of all first order equations. The time to get to 1/2 time is just the log of the number 2 divided by whatever the rate constant is. That would be the half-time. So we can plug in these data and solve for it. And in this, it takes 1114 seconds to reach 1/2 time. And that would be constant throughout the reaction if it's first order. Now suppose we have a second order reaction, and let's suppose that one is, I'm not sure, I don't know. But we can still work the same kind of problems in the second order equation, just use second order data. The rate is some constant times concentration to the second power. That was told us in the beginning, it's second order. And that's going to be equal to this constant times the concentration squared. So if I want the rate, all I got to do is plug that in. Now, remember that's the rate, and this particular, that's the rate of the reaction. But this thing is going twice as fast. So I have to multiply it by 2. So the rate of NOCl is just twice the rate of the reaction, would be this number. The rate of formation of NO would be the same number, but with a positive sign, and chlorine would be half as much. But how long would it take for the concentration of NOCl to go from 0.1 to 0.01, like we did a while ago? So 1 over the concentration at time is 1 over the concentration at the beginning plus KT. We've got our data. 1 divided by 0.01 for this one, 1 divided by 0.1 for this one. This is the rate constant, solve for the time. And rearrange and solve, we get 1.45 times 10 to the 5th seconds. And you see, this, we took the same data and we got a pretty long time because it's second order, it slows down, remember, as you go from 0.1, we would go to 0.05, 0.05 to 0.025, 0.025 to 0.015, which would be close to this one, would be 3 half times. And so that would be a pretty big amount of time for that one. What would be the NOCl concentration after 100 seconds? Okay, again, we use the integrated form of the rate law for second order. It's 1 over the concentration at the current time is 1 over the initial concentration plus KT. And now we have the data we can plug in. We have the initial concentration, we have the rate constant, and we have the time. So we can put these, do the calculation. We get 1 over 0.1 is 10. Plus 6 times 10 to the negative 2 if we take this number times this one. And now we can add those together and then we get 1 over the concentration. So if I want the concentration, I just take the reciprocal and turn this upside down and turn that upside down, divide it into 1. I have 0.0994. So that would give us the initial concentration. How long will it take for the concentration to go from 0.1 to 0.05? That's a half time. So we can plug in the data and you have the 0.05 and 0.1. So this is 20 and this is 10 and this is 6.4 times 6.22 times 10 negative 4. We can solve for the time. it's 1.61 times 10 to the 4th seconds. So now at this point, I can give you another equation for half time for a second order equation. Remember, for a first order equation, the half time is the log of 2 divided by k. Well, for a second order concentration, it's 1 over C initial times k. Now, the C initial, you see, is going to change with each half time. So at one half time, you start out, say, with 1 molar, and then you can calculate what that half time would be. But when you go to the next one, you got 1 over the initial concentration at the beginning of that second half time is 0.5. So it's going to be twice as long. You see where that's coming from? So the relationship is T 1/2 for second order is 1 divided by C0, which in this case is not the very first initial concentration, but it's the initial concentration at the beginning of that particular half time. Okay, that's how long will it take for the concentration to go from 0.05 to 0.025? That's the second half time. Now we said it should be twice as long, so let's just see. Here we put in our initial concentration at this experiment, and the 0.025 is what it is at the end of the half time. 0.05 is what it was at the beginning. We still have the constant. We solve for k, and we do the data, and we get 3.22 times 10 to the 4th seconds, which is twice the first half time. And that's what we knew should happen. Okay, here's some checkpoints for you to test yourself over this and work through the same kind of problems that we did. Okay, so that concludes this particular lesson. And I will stop the meeting now, and I will provide this video to you through YouTube when it's processed, okay? All right, we'll see you soon.